Hi everyone! Today's topic is estimation of uncertainties on unfolded spectra. This is the last piece of the unfolding puzzle. As always, there are two families of uncertainty: statistical and systematic. Let's start with a discussion of the statistical uncertainty. Obviously, it arises from the fact that our data are random variables. Let's emphasize at the very beginning that there are correlations between the values mu sub j hat, between the unfolding estimators of values in the individual bins of the truth histogram. They are correlated despite the fact that the observed numbers of events in bins of the reconstructed histogram are uncorrelated most often. Let's explain why the observed values n sub I are uncorrelated first. The point is that the observed histogram is filled once per event, a particle collision, most often. Of course, different collisions are independent of each other, and therefore an event falling into one bin cannot influence another event to fall into any specific bin. It doesn't influence it at all. There are rare situations in which the observed values in the reconstructed histogram are correlated, though. When you fill the reconstructed histogram multiple times per event, like if you measure the inclusive jet cross-section, then you fill the histogram for each jet in the event. Most likely jet events are dijet, and due to the momentum conservation, kinematic variables describing one jet are correlated with those describing the second jet. Therefore, a jet falling into one bin enhances the chance for the other jet to fall into some specific bin, and hence the correlation between the bin contents. Anyway, even if the observed bin contents n sub I aren't correlated, the estimators mu sub j hat of the truth spectrum are correlated. They get correlated because of the resolution effects. In fact, the response matrix distributes events from one truth bin into multiple reconstructed bins. Unfolding is the inverse operation: estimation of the truth number of events in a bin based on observations in all reconstructed bins. Therefore, a value in one reconstructed bin influences all estimators mu sub j hat, hence their correlations. In conclusion, we always need to estimate the whole covariance matrix for an unfolded spectrum mu vector hat. In the previous videos, we presented several different unfolding methods. However, we haven't touched the topic of covariance matrix estimation except for the maximum likelihood method. We will not do it now either. The individual methods typically provide ways how to estimate the covariance matrix analytically, but we refer you to the corresponding papers. Here we will describe just one method that is general. Great! But that can be costly from the computing point of view. Very sad. We are talking about pseudo-experiments, of course. In short, you generate a large number n of pseudo-observed histograms, assuming that this set of n spectra represents well the PDF for the observed spectrum. Then the covariance matrix estimate is cov hat of mu sub I hat and mu sub j hat is equal to 1 over n, sum over k going from 1 to n, mu sub I hat k minus e hat of mu sub I hat, all this times mu sub j hat k minus e hat of mu sub j hat. Here, e hat of mu sub j hat is equal to 1 over n, sum over k going from 1 to n, mu sub j hat k. There are several ways how to generate the pseudo-experiments. Let's mention two of them. Draw bin content of the pseudo-observed histogram from a Poisson distribution with mean equal to n sub I, the number of events in the bin of the reconstructed histogram. N sub I pseudo is drawn from a Poisson distribution of n with a mean value of n sub I. The second method is called the bootstrap method. In a pseudo-experiment, each event is assigned a weight sampled from a Poisson distribution with mean equal to 1. Effectively, this means that the event is filled once, twice, 3 times, and so on, or not filled at all. In most cases, the bootstrap method is equivalent to the previous one, because sum of Poisson distributed numbers is itself a Poisson distributed number. However, if bin contents of the observed histogram are correlated, then the bootstrap method estimates the correlations correctly, while the other one fails. Let's move to the systematic uncertainties now. The systematic uncertainty on the unfolded spectrum has two main sources. The first one is an imperfect description of our detector in Monte Carlo. It results in an imperfect modeling of the response matrix. The imperfect description of the detector is typically split into many sources, like description of an electron energy calibration, jet energy resolution, efficiency corrections, etc. The impact of each of these effects on the unfolded result is estimated separately by a procedure that is often called propagation of systematic uncertainties. Internally, each systematic effect is parameterized by one parameter. Then, the parameter is shifted by 1 sigma in the Monte Carlo, and a new response matrix is built. The observed data histogram is unfolded with the use of the varied response matrix, and the resulting unfolded spectrum is compared with the nominal result. Their difference is taken as a 1 sigma uncertainty. What concerns meaning of this 1 sigma, an implicit assumption is that in each bin, the quantity mu sub j hat is distributed according to a Gaussian PDF with mean equal to the estimated nominal value and sigma determined from the uncertainty propagation method. Often, plus and minus 1 sigma variations of the underlying parameter are propagated separately. It results in an asymmetric uncertainty on mu sub j hat, and the idea of the corresponding PDF is a two-sided Gaussian. So, these were uncertainties due to our imperfect modeling of the response matrix. What about an uncertainty on the unfolding procedure? We've learned that each unfolding method introduces a bias, and we should check how large the bias is. There are several options, but let's mention just one of them. We can call it a pool test. The pool test is possible just for unfolding methods that provide statistical uncertainties on the mu sub j hat estimators based just on the observed data and not on pseudo-experiments. Moreover, a certain weak expectation behind the pool test is that the mu sub j hat estimators follow a Gaussian distribution. You will see. So, the test now. Take some Monte Carlo reconstructed spectrum. Generate pseudo-experiments from this spectrum and unfold them with the nominal response matrix. Each pseudo-experiment yields estimates mu vector hat together with estimates of their uncertainties. Create a histogram for each estimator mu sub j hat. For each pseudo-experiment, fill the histogram with a quantity called pool. Pool is equal to mu sub j hat minus mu sub j over sigma hat sub mu sub j hat. Sigma hat sub mu sub j hat is an uncertainty taken from the unfolding method. Note that we know the true value mu sub j because we are doing the pool test with the Monte Carlo. For an unbiased estimator mu sub j hat, the mean value of the pool distribution is 0. A non-zero mean value indicates a bias. A standard deviation of the pool distribution different from 1 is an indication of a problem with the uncertainty estimate provided by the unfolding method. A non-Gaussian shape of the pool distribution can mean that the original assumption of Gaussianity of the estimator mu sub j hat is not satisfied. The pool test can be also used for quantities that are functions of the unfolded spectrum. In this case, the pool looks like pool is equal to q of mu vector hat minus q of mu vector over sigma hat sub q hat. Let's review one more unfolding test. The outcome of this test can be used as an uncertainty on the shape of the unfolded spectrum. Let's call it data-driven closure test. Its idea is to prepare and unfold a reconstructed Monte Carlo spectrum that looks like the observed data histogram as much as possible. Then, the unfolded result is compared with the underlying truth Monte Carlo spectrum. A large difference of the two spectra could lead to a change of the unfolding method. An acceptable difference can be used as a systematic uncertainty. The tricky thing might be to get the reconstructed Monte Carlo spectrum with a shape similar to the observed data histogram. For this, take the Monte Carlo with which you derived the response matrix. Reweight its truth spectrum with a smooth function and multiply it with the nominal response matrix. If the result resembles to the data histogram, then you are done. Otherwise, update the smooth function. Let's mention two more common tests of the unfolding. They are quite technical, but they are useful. The first one is just a closure test whose potential is to find bugs in the unfolding procedure implementation. Take it as granted you have bugs in your code. The test is just to unfold the reconstructed spectrum of the Monte Carlo you used for the response matrix construction. If you switch off any kind of regularization, then you should recover the truth Monte Carlo spectrum. The other common test is to unfold various reconstructed Monte Carlo spectra that were generated with different generators, if you have them. A large discrepancy between an unfolding result and the corresponding truth Monte Carlo spectrum could be an indication of a limited validity of the unfolding method. Finally, you should always consider comparing several unfolding methods. So, we are done with the uncertainties and various tests of the unfolding procedure. It's time for a couple of closing remarks now. The first one is about the choice of binning for your truth and reconstructed spectra. Obviously, the more truth bins, the more information about the truth distribution you have. Unfortunately, the more smearing and more statistical fluctuations you face. There is a rule of thumb to choose the bin width equal to the standard deviation of the resolution function. A bit more sophisticated way is to define some criteria on the purity and statistical uncertainty in the bins of the reconstructed spectrum. A question tightly related to the binning you need is the choice of the unfolding algorithm. Up to now, we've been presenting the maximum likelihood method as unusable for unfolding. It was quite unfair, actually. If you are satisfied with very wide bins, and therefore you have high statistics and purity in each bin, then you can use the maximum likelihood method safely. It's not a very common situation, but it can happen. An obvious and important question is CPU time consumption of your favorite unfolding algorithm. Don't forget, you will need to run the algorithm many times, in particular when propagating all sources of your systematic uncertainty through the unfolding. Finally, you will also need to fix parameters of your unfolding method. For example, you can choose the set of values that yields the lowest quadrature sum of the unfolding uncertainty and variance in most bins. With this video, we are closing the course on statistical methods in high-energy physics. We hope you liked it, and in particular that you found it useful for your future career. If you have any questions, don't hesitate to contact us and ask. We wish you good luck with the homework and a good luck with all your exams of the winter term. We are looking forward to seeing you back at the university when the coronavirus crisis is over. Goodbye!